All right, we'll move on. Okay, so today, last week, or not last week you guys took the midterm, and today we're going to talk about sampling distributions. All right, this is it's a slightly different concept from what we are used to, okay? But fear not, okay? I hope you guys are comfortable with the normal distribution, which is from chapter 6, okay? The stuff about, in your midterm, it was the problem with the gorillas. You know, what percentage of gorillas weigh between this and this? Or it was, you know, how tall is a woman in the 30th percentile, or something like that. Those types of problems made a showing on the midterm, and I hope you guys are okay with that, because we're going to see a lot of the normal distribution in the stuff that's coming. Okay, and today we're talking about sampling distributions. All right, does anyone remember what a sample is? Yeah. Okay, what's a sample? Okay, it's data. Why are we dealing with a sample? Yeah.
Because the whole population without the
Okay, so again, well, let's talk. What's a population? That's nothing. Okay, that's one definition of the population, right? The amount of people in a place. But that's not what we're talking about. When we're talking about statistics, what's a population? Everyone we could possibly be interested in. Okay, so it could be, the population could be defined as Americans, so everybody in the United States. Okay, it could be defined as American males between ages 30 and 40. Okay, and that would be all males in the United States between the ages of 30 and 40. It could be defined as all American males between the ages of 30 and 40 that have type 1 diabetes, okay? So it's just a group of people that maybe we're interested in studying, okay? Maybe we're a pharmaceutical company, and we want to study all of the males between age 30 and 40 that have type 1 diabetes. Who knows, okay? That would be the population, everybody we could possibly want to study. But we can't study everyone in the population just because it's too hard to get everybody, and we don't have the resources to study, you know, hundreds of thousands of people. So we have to deal with a sample. Okay. How do we select a sample? Do you remember? Randomly. Okay, and we call that simple random sampling. Good job. Okay. So we select a sample at random. That's simple random sampling. Okay, so we've got a population, which is everyone we could possibly want to study. But we can't study everyone in the population. So through simple random sampling, we select a sample. Okay, this is a select group of people that we've taken from the population. And we're hoping this sample represents the population. Ideally, our sample of the population. Now, let's say there's two companies out there, and they're both interested in studying American males between the ages of 30 and 40 that have type 1 diabetes. Okay? And so, one company says, okay, we've got a whole bunch of money. We hired a statistician. He's going to take a simple random sample, and he takes a random sample of 500 of these patients with type 1, people with type 1 diabetes, American males between ages 30 and 40. Okay. And then the other company says, okay, we've got a bunch of money, and we want to do our own study. So they go and they select another 500 people, again, American males between the ages of 30 and 40 with type 1 diabetes. Okay. Now, think of those two samples of 500 people. Are they going to be the same? No. Are they going to be different? A lot different? A little bit different? How different are they going to be?
Slightly.
Slightly, okay. Well, these are all relative terms, right? So some people might look at this one and say, this is very different from this one, okay? Well, how different are these samples going to be? And if we got a third company that took another sample of 500, that one's also going to be different. It's not going to be the same as these other two samples. But how different is it going to be, okay? So the question is, if we took different samples, how different is one sample from another? Okay, does that question make sense? Okay, if we take samples, different samples from the population, and let's keep all the samples the same size. Okay, if we take different samples from the population, how different are the samples from each other? So if we take different samples from the same population, how different will the samples be from one another? Now we can kind of simulate this just even within our classroom, okay? I don't know how many there are of you. Probably today, maybe around 40, okay? And I could take samples of 5 students at random. And then I could form, here's one group of 5 students. And then I have you guys sit back down. And then I select another 5 students at random. And we can do this over and over and over. And I can generate a whole bunch of different samples of 5 students at random, okay? And each time I mix the students back into the crowd, so it's not that we're limited to a certain number here, okay? How different are the samples from one another, okay? Well, the question is, how are we measuring what is different from one? Like, how are we going to measure whether one sample is different from another? We have to pick some attribute, right? Okay, so we have to just look at one attribute. Okay, so let's say we look at just one attribute. Let's look at one attribute, okay? And let's pick, whatever we want it to be, okay? And let's just compare that attribute from one sample to the same attribute from another sample. And we want to ask, how different are these samples from each other, okay? So it could be, for one thing, we could look at the average, if we're dealing with diabetes, we could look at the average blood sugar levels, okay? We could look at all the blood sugar levels within of each person. and get an average number for the sample. Okay. If we're dealing with this classroom, maybe if we're taking samples of 5 or 6 students, maybe we could say what percentage of the sample is female. Okay, so if 3 out of the 5 students are female, then it's 60% female. Okay, if only 1 out of the 5 students is female, then it's only 20% female. Okay, we can look at how the samples are different from each other. Okay, so if we look at that one attribute from all the different possible samples that can be generated, that's going to create a sampling distribution. Let's just look at one attribute. Okay, if we think of all the possible values that attribute can take, we can get a sampling distribution. Alright. This is it's a tough concept, so I'm going to try illustrating this or demonstrating this with a deck of cards. Okay, so here's a deck of cards. I hope you guys are familiar with a deck of cards. There's 52 cards. Half are red and half are black. So 26 red, 26 black. Okay. So let's just say, well, we could talk about the cards in of themselves, or we could say the cards represent people, and if it's a red card, it represents a female, and if it's a black card, it represents a male, or whatever. Okay. Let's say I shuffle up the deck, and I deal myself 5 cards at a time. Okay? If I deal myself 5 cards at a time, I would have a sample of 5 cards, right? And then I can take a look at that sample, and I can measure the percentage red. Okay? Percentage of cards that are red. So the population is represented by the deck of cards. And from the population, I'm taking a sample of 5 cards. And what I'm going to measure is the percentage of those 5 cards that are red. Let's record the percentage that is red. Okay? And I'm going to call this number, this value p hat. Okay? This is a percentage that came from a sample. So here are 5 cards. I flip them over. I've got 3 red, 2 black. So what percentage red do I have here? 60%. 3 divided by 5, I get 0.6. 0.6 is red. Okay. I'm going to mix these back into the deck. Okay, and I'm going to deal myself another 5 cards. And this time, I got 3 red, 2 black, again. Okay, different cards, but again, 3 red, 2 black. So here is another sample of n equals 5, and my p hat here is 0.6. Mix these up. I'm going to do this again. 5 cards. All right. How many red and how many black? I keep getting 3 red and 2 black. Okay. But what are other possible values that I might get?
2 red.
2 red and 3 black. No red.
Okay, p hat. So here I got p hat as 0.6. But we could imagine if I did this again, I could get a p hat where 2 red and 3 are black. So I would get a p hat of 0.4. What else could I get?
No red.
I could get no red, okay? It probably won't happen as often, but it's certainly possible. And so I could get p hat equal to 0 if I get no red, okay? What else might happen? 1 or, okay. So I could take on, so p hat can take on a bunch of different values, okay? What values do you think is going to be the most common?
2 or 3.
Okay, yeah, 2 or 3 red. So probably 0.6 and 0.4 are going to be most common. But I could also get 0.2 or 0.8 and 0 or 1. Okay, there's different possible values that I could get. And what if I made a histogram? Okay. Well, what numbers go across on the bottom of this histogram? So I'm putting p hats across the bottom. So what are the possible p hats that I can get?
0.
I can get 0, 0.2, 0.4, 0.6, 0.8, and 1.0, right? Any other possible values? No, not with this, okay? And so the p hats that I can take, that I can get are this, and probably 0.4 and 0.6 are going to be the most common, okay? 0.2 and 0.8 will show up, but not as often. And then 0 and 1 will probably also appear, but less often. Okay. So this here, this histogram, which represents all the different p hats I could possibly take. You can imagine I did this 1,000 times or 10,000 times. Okay, every time dealing myself 5 cards, shuffling the deck, shuffling the deck, dealing myself 5 cards, and determining what percentage are red and what percentage is red each time, right? And you can imagine I do this a whole bunch of times, and I keep track of it, and at the end of the day, I make a histogram. I just want to make sure this process is clear to you. Okay? And these are the different values I get. This here represents my sampling distribution. Okay? And if I understood or knew more about this sampling distribution, somebody could ask me, if I deal myself 5 cards, what's the probability that I get all red? Okay. And we can answer that using just the sampling distribution. I could say, oh, okay, well, the probability of getting all red is whatever this number is. Okay. What if I have let's say I bought 10 decks, okay? Or we go to Vegas and they've got the shoe where they've got 8 decks, okay, stacked in there. So just imagine I've got a pile of cards, and let's say I decided to draw out 20 cards at a time, okay? So I draw out 20 cards and I decide to look at what percentage are red and what percentage, I take out samples of size 20 and I look at what percentage are red, okay? So what do you think the most common values we'll see? Okay, so this is another sampling distribution. Again, I got population. This time, maybe I have, we'll say 10 decks of cards. Okay, and I'm going to take out samples of n equals 20 cards. So just imagine this happening. We're not actually doing it now, but okay. So when I take a sample of 20 cards, how many are red? just make up a
12.
number. Huh?
12.
12 cards are red, okay? So 12 red, so that makes my p hat equal to what? 60% red, okay? 12 divided by 20, 60% red. Okay, I take another sample of 20 cards. And let's say I got 10 red. So here my p hat is 0.5, okay? And let's say I do this again, another 20 cards. And let's say I get 9 red. So my p hat is 0.45. Is this okay? And I do this over and over again. Each time taking a whole bunch of samples. Each time taking 20 cards. And I keep track of all the different p hats. Okay, we keep track. All the p hats that I might see. And we make a histogram. What do you think this histogram is going to look like?
More variety than the last one.
Well, what's the smallest value p hat can take?
0.
0, okay? And what's the largest value p hat can take? 1, okay? That's important. We can't go anywhere outside of 0 to 1. Alright, what do you think the most common value p hat's going to take?
0.5.
0.5, okay? Not 10. We'll probably see 10 red cards out of 20 cards the most often, but that's not p hat 10. P hat is 0.5 in that case, okay? So 0.5 is probably going to be the most common value. Other common values will be when I get 11 red cards or 9 red cards, and that would be p hat is 0.55 or 0.45, okay? And so basically, when I'm close to 0.5, it's going to happen quite a bit. And the further I get away from 0.5, it will probably happen less and less often, okay? And so I might get a shape that looks kind of like this. Does this look familiar?
Yeah.
Okay.
Symmetric.
Yeah, it's symmetric.
Unimodal.
Exactly. Unimodal. And
It looks like
it should look like the normal distribution. Normal distribution, okay? And this is a neat thing that happens, is that when we look at proportions, okay, if we repeat this experiment, whether it's with decks of cards or people, okay, let's say we choose 50 random people from the United States, and we're looking at what proportion are men and women, okay? If we keep track of it, it's going to look something like this, okay? We're going to have something that looks a lot like the normal distribution. And it doesn't have to be centered at 0.5. Why is this one centered at 0.5?
Because black and red are even.
Yeah, because half of the cards in the deck are red, and half of the cards in the deck are black, okay? But just imagine I had 10 decks, and let's say I wanted to ask, what proportion, I take 20 cards at a time, what proportion of the cards are clubs, okay? Every time I look at a pack of 20, I'm counting what proportion are clubs, okay? Then that distribution will be centered where? 0.25. 0.25, because 1/4 of the deck is clubs, okay? So whenever I draw out a pack of 20 and I count the proportion that are clubs in my sample, maybe I get more than 25% clubs, maybe I get something less, but it'll probably be around 25% clubs most of the time. Okay? Does that make sense? Shake your head no. Okay, so let's talk about, yes.
Just going back for a moment,
when you were going through this histogram, I mean, you said three things. You said, you see this is unimodal, it's symmetric, and then I believe you said
Normal distribution.
Yeah, it
normal
fits the normal distribution.
Thank you.
Okay. Now, I mean, there's a few warnings that I got to say before we say normal distribution. Okay, but we'll talk about those. Talk about those. Okay, there's a few terms and a few letters that we've got to call attention to and make sure we understand the difference between, okay? One thing we talked about was p hat. What is p hat? Not a probability. Okay, where are these p hats coming from?
It's a percentage.
It's a proportion from our sample, okay? And so when we took a sample of 20 cards or a sample of 5 people or whatever, it's the proportion that we got. That's our p hat, okay? Sometimes we call this the sample proportion. Okay, that's p hat. This is different from P. P is the proportion in our population. Or sometimes we just call it the population proportion. Okay. So when we're talking about a deck of cards, the population proportion for the proportion that's red is 0.5. So when we're talking about a deck of cards, half of the deck is red, that's our population. So the population proportion P is 0.5. But then when we talk about P hat might be 0.5 if we get 10 out of 20 red cards. It could be 0.45 if we get 9 out of 20 red cards. It could be 0.6 if we get 12 out of 20 red cards. Okay? So p hat could take on different values, but p is fixed at one value, and that's whatever's in the population. Yes?
I just got a little confused, so I want to see if I got it right.
Okay.
So P would be like, how you said the clubs would be 0.25.
Yes.
And then, so it depends how much your, like red would be half of it, and then any type of, like a club of diamond would always be 0.25 because there's 4.
Right. I mean, it depends whatever. I mean, I could just say in our population, this is the proportion that exists. Okay? So if I talk about, if I say in Los Angeles, I don't know, let's say 40% of Los Angeles is white, okay? Then our P, if we were talking about the proportion that's white, would be 0.4. That's fixed. If I take a sample of 100 people and I calculate P hat, that number could be any value. It could be, I could get 33 out of 100 people being white. Okay, I could get 45 out of 100 people being white. That's going to be my P hat. That value will be different. But the P in the population is set at 0.4. Eric.
In most real situations, like what you said,
Yeah.
40% of people in LA are white.
Uh-huh.
Did we not find that out by taking samples and putting them together?
Okay.
Yeah.
That is where we're heading next in the future, okay? So this week we're pretending that we know what exists in the population, okay? In reality, we don't know, okay? But that's going to be where we're going in the future. In the future, we're going to say, I don't know what exists in the population. How can I figure that out? But today we're going to, that's actually even later today. We're saying, let's pretend that we know the population in Los Angeles is 40% white, okay? For the deck of cards, we know, that's easy. We know that half the deck is red, okay? But yeah, you know, in Los Angeles, we don't actually know the percentage that's white, okay? Well, we can take good guesses. But today we're going to pretend that we actually know these values, okay? Okay, N, of course, is what?
Sample.
The size of the sample. Size of the sample. Okay. Anything that comes from a sample is known as a statistic. Anything that describes the population is known as a parameter. Okay? So statistics are calculated from samples and parameters define the population. Okay, so p hat, is that a statistic or a parameter? Statistic. And p is a parameter.
All the time,
Yeah, all the time. Is this
So, from your example of 40%, so a parameter would be race?
no, parameter would be 40% of Los Angeles is white. The parameter is 40%.
Okay.
Okay, that describes the population of Los Angeles.
So it's a
It-
numeric value? Or
Yeah, it's P, right? P is a proportion, okay? I mean, it could be other, it doesn't have to be, so here we're talking about race, which is a categorical variable. It also exists for numeric variables, okay? But here it's a proportion, P,
I understand.
okay? And that's a parameter. Okay, so let's, let me pose a question to you guys. Alright, hang on, you guys. Something interesting happened, but okay, so let's say we know that 40% of Los Angeles is white. Okay? Let's just say we know this. Alright, let's say we task someone, we put them on a mission, and we say, okay, go out and take a random sample of 100 people. Alright? And they actually somehow pull off simple random sampling. Okay? Let's also say someone takes a random sample, takes a truly random sample of 100 people from Los Angeles. Okay? What could the p hats of this sample be?
0 to 1.
Okay, p hat could technically be any value between 0 and 100, right? What do you think? What's a likely value for p hat? 40%, okay. Is 41% likely?
Yeah.
It's pretty likely. What about 38%? Sure, okay. 50%?
Yeah.
Maybe. Okay. Is it possible to take a sample where we get 60% white?
Yeah.
Okay. But how? No, I mean we're taking a truly random sample. A truly random sample. Okay. It's not depending on what neighborhood, because that's not a random sample. Okay. Because we're taking a truly random sample, so it's not that we've mistakenly sampled wherever white land is. Okay. We're taking a truly random sample, so every single person in Los Angeles has an equal probability of being selected. Okay. So it's if we see something, it's not because we've made a mistake in the sampling. All right, that's an important distinction. Okay, so if we're taking a truly random sample, is it possible for us to get 60% white? It's possible, but is that going to happen often?
No.
Probably not. Okay, is it possible for us to get a truly random sample where 90% are white?
No.
I mean, it'll be very, very, very unlikely, okay? And I'm telling you, if you took a truly random sample of 100 people from Los Angeles, you're more likely to win the lottery than get 90 white people, okay? Out of 100, where you're getting 90% white, because the statistics just works out that way, okay? And I'm not trying to say anything strange here, okay? It's just, that's how the thing works, okay? So let's think of the possible values of p hat, okay? Think of the possible values of p hat. Think of the possible and the plausible values of p hat. So I'm going to ask you a question. What is the probability that a random sample of 100 Angelinos, 100 people from LA, has a p hat proportion of white people, p hat bigger than 55%. Can we figure this out? Yeah? Okay, well, yes, the answer is I wouldn't give you a question like this if we can't figure it out. So I will tell you right now that when we're dealing with a sampling distribution like this, okay, we're going to get something that looks like the normal distribution. Okay. This normal distribution represents the different possible p hats that I can get. Okay? This is the sampling distribution of p hats. Again, how are we getting this sampling distribution? What does the sampling distribution represent? What does this sampling distribution represent? It represents all the possible values of p hat that we can get from all the possible samples of 100 people that we might get from Los Angeles. Okay? So you've got to think there's a very large number of samples of 100 people that we can get, right? If we just randomly select 100 people from Los Angeles, there's a whole bunch of different samples that I might possibly get. This represents all the possible values of p hat that I might get, okay? And it's going to look like a normal distribution. What is the number? Okay? If those of you know it right away, don't blur anything out, okay? Think, what number will go right here in the middle? Okay, just think about it. Okay, yeah, the mean goes in the middle, but what is the number? If we're talking about the proportion, this p hat is the proportion of people in our sample that's white, right? So we might get, we might get 55 people that are white and our p hat would be 0.55. We might get 30 people that are white and our p hat would be 0.3. Think of the value that might go right here in the center of this normal distribution. You guys have a number in mind?
Yeah.
Okay. That number is 0.4.
Explain that.
Explain that. Okay, what number did you think was going to go there? 5? 0.50? Okay. Now why would you think 0.50? Okay. Well, I'm putting 0.40 there because I said 40% of Los Angeles is white. Okay? So if 40% of Los Angeles is white, whenever I take a random sample of people in Los Angeles, I'm expecting 40% to be white. So that's the average of my sampling distribution. Remember, this is the different possible values of p hat that I might get. When I take 100 random people and I count how many people are white and I figure out the proportion that's white, okay, maybe there's 43 people that are white and my p hat would be 0.43. Does that make sense? Okay. Or maybe I take 100 random people and 25 people are white and my proportion there is 0.25. The number that's going to be most common that goes in the middle is going to be p hat is equal to 0.4. Does that make sense? Okay, and that's because I'm telling you that the population of Los Angeles is 40% white. I don't know if that's actually true.
No,
It's
but
probably
I get
somewhere.
So if
Okay.
it's 20%,
It would be 20%, exactly. Yes.
Again, how did you say that we know it's normally normal distribution?
I'm just telling you that, okay? You just got to go with me, and there will be a few things where we can say, is this going to be a normal distribution? But just for now, just trust me that it's going to be normal. Yes.
If we have data that is always symmetric and unimodal, does symmetric and unimodal mean normal distribution?
No, it doesn't mean that. Okay. That's a good question. Okay. All right. So here we've got this. Okay. There are two things that we need. There are two parameters that define a normal distribution. One is the mean. What's the other one? The standard deviation. So we got to know the standard deviation of this sampling distribution. Okay. So this is a normal distribution. The mean of this normal distribution is equal. What was it equal to? 0.4. And if I want to use the symbol, what symbol represents 0.4?
Like that U. Like
Okay,
that.
well, mean,
Oh,
the
is it
mu
mu? Yeah.
represents the mean, but if I'm talking about stuff, the 0.4, this is P. P, the sample, and not the sample, the population proportion, right? This is the proportion in Los Angeles that's white. This is my population proportion, P. Okay? My standard deviation, sigma. Okay? And you just gotta hang with me here. Alright, I'm just gonna put up a formula. It's equal to P times 1 minus P divided by N. Okay? So, someone go on their calculator, figure this out, or actually everybody should see if they can figure out what the standard deviation is, and I will tell you what it is, okay? Good opportunity for you to check your understanding.
Yeah, what was our sample size?
Isn't it 100? It's 100,
Samples
right?
of size 100, yeah. Of 100 people. Okay, so when you plug in the values, I'm hoping this is the number you get. Is that what we got?
Yeah. Because basically, you just rounded it, right?
Yeah, I just rounded it. Is that okay? 0.049. 0.4 times 0.6 divided by 100 square root. Okay, so now that I have these pieces of information, can I answer this?
Yeah.
Okay, so try to answer this original question. What is the probability that a random sample of 100 people from LA has a p-hat greater than 0.55? Or is that too much of a leap task?
No. So,
Yes.
would you do 1 minus that, since usually we find, like, cause I remember before we would always find what was less
I got that.
than mean.
No, this is a standard deviation, and that's a mean, right?
Oh.
That's a standard deviation, and that's a mean. So the answer to this question down here,
Oh, Z-score. You find Z-score.
alright, stay with me, you guys. I got 0.40 in the center, and I'm drawing a line where? 0.55. And I want to know, what is the probability that a random sample of 100 people have a p-hat of 0.55 or more? We got to find a z-score. And z is equal to what? 0.55 minus 0.40 divided by 0.049.
3.06.
3.06.
Yeah.
Great. Is that my answer?
No.
No. Okay. I told you not to pick this answer in the midterm. Some of you guys did. All right. So what do I do now?
Go to your chart.
I got to go to my z table. I got to go to my z table and look up how much. Yeah, I can either look up negative 3.06 and take the number there. Or I can look up 3.06 and subtract that from 1. Point 0011. Okay. So that this area here is 0.0011. Okay. So if you take what this is saying is that if you take a random sample of 100 people from LA, what's the probability that you're going to get 55% white or more in that sample of 100? That's only going to happen about 1 in 1,000 times, okay? It's a very rare occurrence. You can take a bunch of different samples of 100 people, and the probability of getting 55% white or more is about 1 in 1,000, okay? And that's because the overall proportion of LA that's white is 40%. And so to get 55% is rather unusual. That's what this is saying. Does that make sense? Okay, so I'm just going to ask a quick follow-up question, make sure we understand this. Alright? If you take a random sample of n equals 100 people in LA, what is the probability that p hat is less than 43%, 0.43. Okay, see if you guys can answer that. You have a question, yes? I looked at 3.06, and what did you get? You see 0.9889. So z is equal to 3.06. Gives me an area of 0.9899, right? Okay, but I want the area to the right, so I'm going to do 1 minus that. And I get 0.0011. Oh, 9889, sorry. Okay, see if you can answer this question over here. You take a random sample of n equals 100 people in LA. What's the probability that p hat is less than 0.3?
Is this still assuming that we know that 40% of LA is...
Yeah. We're still assuming that 40% of LA is white. Okay, p is equal to 40%. Yeah, we'll do more examples. Okay, put the answer up here. Isn't that right? Sure it's right.
Is that right?
Yeah. You guys need another moment, or okay, this is our answer here. So how do I answer this question? So we're still dealing with a sampling distribution because we're talking about p hat, right? What is my mean? My mean is still 0.40. Okay, and what's my standard deviation? It's still 0.049. Nothing has changed. My p and my n's are all the same. And where am I drawing my line? At 0.43. And I'm asking what's the probability that p hat is less than 0.43. So I get a z-score, 0.43 minus 0.40 divided by 0.049. And I get a z-score of 0.61. I look up 0.61 in the Z table, and I get 0.7291. Doing 0.43 minus 0.40 minus 0.049.
How do we know to cut it off?
Well, because when you look it up in the table only goes out to 2 decimals. Okay, make sure you're doing the order of operations correctly. Okay. So you do 0.43 minus 0.40 on the top, entirely divided by 0.049.
No, I know. When I did it separately, like I did 0.43 minus 0.43 minus 0.40 divided by 0.49. But I did it all at once. I had to do it
Okay.
separately.
If you can do it all at once, but you got to do this then. Why do we have to do this? Because of order of operations.
No, I know. That's how I did it.
No, if you what you did was this. Okay, this doesn't work because
it's thinking I'm doing.
it's going to do the division before the subtraction. So here you've got to force the subtraction first, and then allow the division through the parentheses. So that's order of operations. Okay. Let's try another example. Okay. Okay. Let's say I have a coin. I have a regular old coin. And I'm going to flip it 30 times. It's a new game in Vegas. It's called Flip the Coin. Alright? You gotta flip it 30 times. It's very exciting. Okay, flip the coin 30 times. If you get 20 heads or 20, let's just say if you get 20 heads or more, you win the game. Okay? You flip the coin 30 times. If you get 20 heads or more, you win the game. Okay? Simple enough, right? Flip the coin 30 times, 20 heads or more, you win. Okay, so what's the probability of winning this game? No, stop. Stop blabbing off answers that okay. You guys said something like 0.60, right?
Yeah.
Is that, huh? Or I don't know, what's the number that somebody's tried? Nobody said anything? Nobody said anything, okay. I'm just hearing things, okay? Well, if somebody said 0.60, just think about that. Does that make sense, right? 0.60 means you've got a better chance of winning than losing, okay? And that means playing flip the coin once is a worse game for you, okay? You flip the coin once, you win if it gets heads. There, you only have a 50% chance of winning. If here you're going to have a 60% chance of winning, this game is way better, but it's clearly not, right? It's clearly not. Okay, so you're going to flip the coin 30 times. If you get 20 heads or more, you win the game. What's the probability of winning the game? Can we answer this?
Sure.
Sure. Let's try it. Okay. what are we dealing with here? What proportion heads do we have to get in order to win?
20 out of 30.
My p hat has to be what?
20 or greater.
Like 0.66 or 0.67 or higher, right? So p hat, so to win, p hat has to be greater than 0.67. Let's just say that. Is that good? What is the distribution of p hat? It's a sampling distribution.
0 to 1.
Okay. Well, p hat can take on any value from 0 to 1. That's true. But this
Oh, it's normal distribution?
it's going to be normal. What is the distribution of p hat?
Is it 0.5?
That's not the distribution of p hat. It's the center of the distribution. So p hat is going to follow a normal distribution. Are we okay with this? I'm-
Yeah.
No. Okay. So I got two people shaking their heads, but which I appreciate, okay? Because I got, I got a student who's saying, yeah, we're good, but then everybody else is quiet, so I don't know. I don't know what's going on, okay? So you guys are shaking your heads, so I appreciate that, okay? So can you just tell me what's giving you a little bit of trouble here? Okay. Because we want 20 heads out of 30, right? This is coming from the winning condition. We have to get 20 out of 30 heads to give you 0.67. Okay. Huh?
I said that in the beginning.
Yeah. Okay, but that's not the probability of winning.
Yeah.
Okay. I thought you said nothing, right? Okay. What we're saying is, what is the distribution of p hats? Okay, so every time you play the game, you're flipping the coin 30 times, and if we count the number of heads you get, or the proportion of heads you get, you might get any value, right? Maybe you get 10 heads, maybe you get 15 heads, maybe you get 18 heads, okay? If you get 18 heads, your p hat is 18 divided by 30, 60% heads. Is that good? But here, we want to know what are the possible different values that p hat can take. Okay? So p hat can take on any value between 0 and 1, but specifically, it's going to look like the normal distribution. Okay? P hat is the proportion of my sample that's heads. What do you think is the most common value that I'm going to see? 0.5. Okay? I should probably said everybody think of a number. Okay? But that's okay. All right. 0.5. Why am I putting 0.5 here? Okay, 50%. What is 50%?
Your chance of getting hit.
0.5 is my p. P is equal to 0.5.
Why is that?
All right. What does p represent?
The population.
The probability or the proportion from the population. What's my population?
0.5.
My population is not 0.5.
This has a correlation is
My population is all the possible outcomes of flipping a coin, okay? And what's the probability that a coin lands heads when I flip a coin? 0.5. So my p is 0.5. This is a fact that exists from the coin flip. P is 0.5. So when I flip the coin 30 times, maybe it will land heads 50% of the time. Maybe it will land heads more than that. Maybe it'll land heads less than that. In order for me to win, the proportion that it lands heads has to be what?
0.6.
It's got to be 67% heads or more, meaning I got 20 out of 30 heads. Yes. Okay. My might die, but we're gonna get this eventually. So I want to find 0.67, and am I gonna shade this area or this area? To the right. Because I want to know what's the probability that I get 67% or more. Okay? What's my standard deviation? I don't know. I don't think it's 0.01. I don't think it's 0.01. I think it's got to be something different. A standard deviation. It's my standard deviation, right? My sigma. Okay. So I'm going to put in, what is P? 0.5. And 1 minus P, which is also 0.5. And what's N?
20?
Huh?
30.
30. I'm flipping the coin 30 times. Okay? That's the size of my sample, 30 coin flips. So my standard deviation is 0.091, I believe. Okay? 0.0913. Okay, at this point you guys should be good, right? Okay, so tell me what the answer is. Okay, or figure out the answer, write it down, and then I'll put the answer up on the board. Okay, because if we're not good with the normal distribution, all hope is lost. Okay, I shouldn't say all hope is lost. All hope for this class is lost. For the rest of your life might be very bright and beautiful. But if we're not good with the normal distribution, this class is going to be a disaster. Good, Eric? Alright. At least I can trust, count on some people. Yes? You should always keep 2 decimals in the z-score, okay? Don't go to 1.9. Okay, z-score 1.86. The area in my tail, 3%, 0.0314. How are we feeling? Yes.
You got that number because you did 1 minus 0.9686, right? Because that's what you got when you did the chart?
Yes,
Okay.
yes, 1 minus that, exactly. Because on this side I get 0.9686, yeah? But I don't want 0.9686, okay? Doesn't make sense that the new game in Vegas has a 97% chance of winning, okay? Everybody would play, and they'd lose all their money, okay? 3% chance of winning, okay? Sounds simple enough, right? Flip the coin 30 times, all you gotta get is 20 heads or more. Chance of you winning It's only 3%, okay? Okay. Let's take a little break, and then we'll come back and talk some more.